Chapter 4, Part B, Thermal Expansion, Sample Problem 1. Solid bodies in general experience either increase in temperature or decrease in their temperature. So the first one goes by thermal expansion, and likewise the other one goes by a thermal contraction. As if we do have a original sample, if the temperature goes down, if you cool a material, it just shrinkage, and if you heat it up, it just expands at both ends. Likewise, we call delta T thermal, either expansion goes by a positive, or contraction, decrease or increase of length due to temperature, is a consists of alpha, a coefficient of thermal expansion, over each degree of Fahrenheit or Celsius, times delta T, change in temperature, either decrease or increase, times the original length of the material. Let's put it in an example to verify. Just consider we do have a column with a square cross section. So it's a cube in 3D and a square in 2D, goes from supported in two fixed support at A and B. The material is A36 steel and is constrained between two fixed support at the bottom and its top. So when the temperature at initial condition is 60 degree Fahrenheit, when we heat it up to 120 degrees Fahrenheit, we just want to see what is the average normal stress, thermal stress in the structure. And the cross-sectional area is provided by a 0.5 inch times 0.5 inch at these dimensions. And as soon as we know the material, we can go to the table of material properties, go by modulus of elasticity for that material, which for A36 steel goes by 2910 times 10 cube KSI, and the alpha thermal expansion coefficient is 6.610 to negative 6 over degree Fahrenheit. Let's approach the problem. In this kind of problem, the easiest approach is to release one end, and due to thermal increase, the material tends to expand. If we release one of the supports, for example support B, it just tries to expand by the amounts of delta T, which stands for delta deformation due to temperature. Mhm. And at the same time, in a real scenario, because the B is fixed, we just let it to we just release the support B to see the effect of the increase in temperature, increase due to temperature. But in the reality, the uh, point B goes nowhere with respect to A. So in that case, there is a downward push at both end A and B, which tries to pull push the material, push this B back to the original location of B. So delta T plus delta F and goes 0. So from equilibrium equation, summation of forces in y direction should go 0. So Fa is equal to Fb, force at support A is equal to force at support B, and both of them are equal to F. So the problem is symmetric, so both of them are identical to each other and goes by F. And the other piece of problem solving is a compatibility, which says delta A with respect to B goes 0. It says B in reality it goes nowhere with respect to A. B goes nowhere with respect to A because both ends are fixed. So, and if you want to put that in the language of math, that says the delta T increase in length due to temperature minus delta F decrease due to push of support should go 0. Delta T is the equation is alpha delta T times length of this specimen minus this is positive expansion goes by positive for delta T goes up, delta F goes down. That's a push, which is negative. FL over EA, which is delta in axial condition, that goes by NL over EA, and just N replaced by F goes 0. So the only unknown, if you cancel out L, the length from both sides, the only unknown of L goes to be F force is going to be thermal force is alpha delta T times E of times A. Let's let's put it in a example to see how it works and if you replace the numeric value for our problem, our case, F is a coefficient of expansion, which is provided to be 6.610 to negative 6 times increase or delta in temperature, which goes from 60 to 120 and a delta. So that's our alpha times delta T. This is our cross-sectional area, which goes by 0.5 inches squared times modulus of elasticity of A 36 steel, which is 29 10 cube KSI. And if you do the math, it just gives you the numeric value of force equal to 2.871 kilopounds. As soon as you know the force, stress is force over the area, and you get a numeric value of thermal stress of 11.5 kilopound square inches.